Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on this course on control systems. In the previous lecture we have seen these two interesting transfer functions, namely the complementary sensitivity and the sensitivity functions, particularly for closed loop systems. Prior to that we saw that when you actually want to put an open loop transfer function into a closed loop configuration, then you have to consider at what stage you are going to drop off the additional poles and zeros so as to be able to approximate the overall system as a second order system, which will then bring to play all the things that we have learnt about the performance metrics of second order systems. So we discussed why these poles and zeros should not be cancelled or eliminated, I mean the additional poles and zeros, in the open loop stage. Only after they are put in this closed loop configuration should we think about whether we can drop off these additional poles and zeros. Okay? And then subsequently we saw that the role of this unity feedback structure is of particular importance and interest to us, mainly because it leads to these interesting transfer functions, as I said, the sensitivity and the complementary sensitivity, which then gives us a goal for controller design in the frequency domain. Now of course we haven't really spoken about controller design at length, we haven't even spoken about what frequency domain is. These will come later and then these discussions will be clearer at that juncture, but for now it suffices to understand that the sum of the complementary sensitivity and the sensitivity is unity irrespective of what the value of S is. Later on we shall see that this S will be some j omega, where j is of course the square root of -1, so it is going to be only a purely imaginary number, and that makes sense because we will be considering the steady state behavior of systems. Alright. In such a case we let S take purely imaginary values and analyze the magnitude and the phase functions of those transfer functions, okay, but all that will come later, all in good time. For now we were interested in seeing how different closed loop configurations can be massaged and brought down into this typical unity feedback structure that we are familiar with or that we have studied at some length. So on our pursuit along this direction we actually saw that when you have a configuration such as this, where you could have the input coming into a summer at any arbitrary location in a loop and the output could be any arbitrary pick-off point in that loop, right. In that case you partition this loop into two parts, one part being G forward, the other part being G feedback, right, and in that case the transfer function corresponding to that input output pair can be very conveniently written as G forward divided by 1 plus G forward times G feedback, all this under the assumption that it is a negative feedback, that is what causes this positive sign here. Alright. The interesting thing that I drew your attention to towards the end of last lecture was that notice how irrespective of where the input is coming into the loop or where the pick-off point signifying the output is being demarcated in the loop, this denominator is going to be always the same. In other words, it is going to be the product of all the blocks that you come across as you go once around the loop, okay, and this is of exceeding significance particularly in this course, right, because this is what will give rise to all our controller design goals and will crucially help us in studying this important thing called stability. How so? Just to give you a brief glimpse into this, look at this closed loop transfer function here, alright. If you look at this closed loop transfer function, what are its poles? because we have seen that stability is solely governed by the poles of the effective transfer function. So here, since we are concerned with the closed loop behavior, so we will talk about the closed loop transfer function and its poles. So notice how if we wanted to evaluate the closed loop transfer function's poles, we would have to solve for this equation. Of course, I have dropped this variable s, right. So of course, g forward is a function of s, g feedback is a function of s, both of these are typically rational functions of s, right. So when we have to solve for this, so let us call this the star equation, okay. So solve for this star equation, yeah, and check out if all of those solutions are on the left half of the complex plane. If they are, then the system is closed loop stable, okay. Now there are ways of determining, okay, this is not something that has to be given to a control engineer, okay. A control engineer worth his or her salt should be able to determine, given a transfer function like this, a closed loop transfer function, as to whether, yeah, that transfer function is closed loop stable, okay, that system is closed loop stable. So there are ways of doing this, we shall shortly be venturing in along those directions. In fact, we will be studying several methods, okay, even without using computers or solving for roots of polynomials using computer programs. We will see that there are some very, very elegant and beautiful methods to actually be able to ascertain as to whether your closed loop poles are all of them on the left half of the complex plane or not. Okay. So enough for on that account, we will revisit stability, and this will keep popping up time and again. For now, just as we did for our performance metric study of second order systems, we will assume that the system is closed loop stable, because in what follows, the things that we will be studying will only make sense if the system is stable. We will be studying the steady state behavior, the errors arising in a system that is put in a closed loop configuration. What sort of errors? So we will take this reference signal as our input, and we will track the output, monitor the output, and take the difference between the two, which is basically the variable that drives the system, okay. This is basically r minus y, and that is why we are in love with this unity feedback loop, because there that r minus y is clearly seen to drive the system, okay. So this r minus y, we want it to go down to 0. In other words, we want the output to perfectly track the input or the reference input, okay. So that is the servo problem. So all of this will only be possible if the system is fundamentally at least stable. If it is not stable in closed loop, then none of this will make any sense. So for until that point where we actually venture into the discussions on stability and what makes a system stable or unstable, right, or what the conditions for stability or instability, we will always, without loss of generality, assume that the system given to us is closed loop stable unless otherwise specified, okay, and then we will carry on with our analysis. Okay, so enough said. Now remember what we were actually discussing towards the end of the previous lecture. Our goal was to basically reduce a block diagram to a convenient form that we are familiar with, which is basically this unity feedback form. And we saw that the different kind of elements that we encounter as we embark on this mission are summers, pickup points, and blocks representing dynamical systems, like so, okay. So what sort of combinations can we encounter? One is of course this combination that we have seen, and I have told you that this is going to be the effective closed loop transfer function between the input r and the output y, alright. Now this is not all. Now what if you actually want to now see this as an equivalent unity feedback? How do you do that? So here is how. You see, once you have reduced this block diagram to this form, this can now effectively be lumped together in this form, where this we call G forward, again I am omitting S for brevity's sake, and this we call G feedback, alright. Yeah, so this is a very standard configuration. So latent within all of this is the fact that we have merged together these different terms, we have taken their products. That will come a while later. Of course, you already understand it intuitively why we are taking these products, but we will see that configuration shortly. We will not leave anything to doubts. Okay, So let us say we have already managed to get it in this form, but we actually want to see it in the following form: some effective g like so, the same y here like so, and this E, this is of crucial importance to us, because this E is basically going to tell us what the difference between the reference input and the output is. Okay. So that is why we want to get from this configuration to this configuration, from this configuration 1 to this configuration 2. So how do we do that? Okay. So one way is, of course, you add and subtract 1. How so? For instance, from this pick off point you take a unity gain like so, and you add it here as a +1, and then take another from the same pick off point, right, and you take a difference, right. Now look at this, what happens if I focus on this part inside the blue box? Okay. So I am going to do this. Now there is this G forward here, let me draw that. So of course the summer I can split up, right. So instead of summing all the 4 signals at this one summer, I can split this up into multiple summers. It is really a no brainer there, isn't it? Right. So this is Y of S, so then there is a G feedback here, right, and at the same time there is this -1 here, yeah, and all of this we are going to sum together here. So this is a -1, it is a negative feedback, right, and this is also a negative feedback, all right. Now we are going to draw that green line. So this is the green line, which is the additional feedback that comes in here, yeah. So let me redraw this, yeah, this is R of S. So now what I am saying is that instead of looking at this original block diagram, what we now focus on is this fellow, and if we can reduce this fellow, to be equivalent to this, then we are done. But look, that is not really a big deal, is it? Because now what you have here is a G feedback and a -1 in what is called a parallel path. So that is next the problem before us. So what do we want to understand? We want to understand if there is this one transfer function G1, there is this other transfer function G2, and if they are summed at a location like so, yeah, then what is going to be my, so this is, let us say, R is being fed to both of these channels, all right, and this is my YS coming out of this summer. So the question before us is then, what is going to be the overall equivalent transfer function for this, all right. So a moment's thought will tell you that it is really not that difficult, because you see what is at the output of this block G1, it is nothing but G1 times RS. What is at the output of this block G2? It is nothing but G2 times RS. So what you are summing out at the end of this summer is G1 times RS plus G2 times RS, right. So what is this YS? This is nothing but G1 times R plus G2 times R. In other words, I can simply reduce this to the following configuration: G1 plus G2, yeah, and this is my R, and I am done, right. So that is a parallel equivalent. While we are at it, let us also take the cascade equivalent. Some people also call this the series. So cascade equivalent, so for example you have G1, of course we have already done this before, very intuitively, yeah, Gn. suppose you have multiple such blocks in cascade and you have R here at the end and Y here at this end, the output end. So you want to find out the transfer function from R to Y. How do you do that? Just name these intermediate variables as x1, x2, x3, so on till xn. So what you have then is xn is equal to y, yeah, and x1 is equal to g1r, right. What is x2? x2 is equal to g2 x1, right. So you proceed on like this till you get xn is equal to gn xn minus 1. So notice that xn is equal to gn x minus 1 and that is also equal to y, yeah. So putting together all these equations, you will see that what you eventually then get, yeah, is that y is equal to gn xn minus 1 is equal to gn times gn minus 1 xn minus 2, so on until you come to the final stage where you have gn minus 1 dot 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 till g1 r. So the overall transfer function then becomes this product. So again I might warn you that when you are dealing with seesaw systems here, it really does not matter in what order you multiply, but the way I have shown you here, this is actually applicable for a multivariable system as well, right, where of course these could be multiple inputs, multiple signals flowing in between these blocks, alright. So therefore this order will be of significance when you are dealing with multi-input, multi-output systems, okay. So in general it is a good practice to respect this order of multiplication, although again for seesaw systems it matters not, right. So therefore you see the way to remember this is from left to, as you go from left to right here, the order of the multiplication is reversed here. That is a quick way of remembering, but of course you do not need these quick ways if you have the concept clear, which is how this is derived, and that I have already shown you, right. So we have seen the parallel equivalent and the cascade equivalent. Now let us go to the problem on hand, which was this. So here what do we have here? This is after all nothing but a parallel equivalent, right, this G feedback and this minus 1. So why not reduce it to this, right. So then we have this R and we have this typical unity feedback which we have already extracted, right, and then we have this plus and minus, right, and instead of this G feedback we now have this G feedback minus 1 and you have this G forward, okay. Please excuse the drawing, it is because of the shortage of space that I am drawing in this fashion, right. So now notice we are in familiar domain. Why? Because now this block I know how to handle. In fact this is nothing but a typical feedback block which we have already seen what it leads to, right. It leads to this G forward over 1 plus G forward times G feedback. So why not write this block down? So then what I will have is basically G forward upon 1 plus G forward times G feedback minus 1, yeah. I can easily treat this as my equivalent, remember not the actual open loop plant transfer function, but the equivalent open loop. So this is the equivalent open loop TF for unity feedback, okay. So now remember, if someone asks you that okay I have given you this plant along with this structure, this closed loop structure which is typically not in this unity feedback loop structure, okay, unity feedback closed loop. So what do you do? How do you analyze these variables? How do you obtain these complementary sensitivity and all this, okay. So you do not go about just blindly taking this RS minus F G feedback times YS, okay. You remember that the idea is that you have to get the difference between R and Y somehow or the other. So that is why you must focus on this particular transfer function for all of your studies, okay. This is now going to be treated as the equivalent block here. So this you substitute here, alright, and then carry on with your usual investigations, okay. So that is what I wanted to discuss. So in the process we have also discussed this parallel equivalent and the cascade equivalent blocks. There are a few other tidbits here that need to be discussed. So often you might have to do some other tricks rather than just this parallel series equivalence, okay. So for instance, you have, let's say, a summer here, and let's say one signal R1 coming in here, and let's say another signal R2 which is coming after being multiplied by this G here, alright, and you want to actually push this G inside, okay. So you want to reduce this to a structure where you only have R1 and R2 coming here, and you want to push this G in here, right. So what do you have to do? Notice that this R2 does not have to change really, right. But what about R1 now? Yeah, R2 was already being multiplied by G. Yeah, so what was coming as the output was R1 plus G R2. But on the other hand, for R1, you cannot let it pass through G, right, because in the original system R1 wasn't passing through G. So what you do is you multiply this by 1 by G. Yeah. So if you want to push this block inside, for the one for which there is this block present, you have to do nothing, but for the ones where this block is not present, you have to adjust it with its reciprocal, okay. So similar process, I mean these are equivalent process, so I might as well draw both ways. So sometimes maybe you have this block here and you want to pull it out, right. So again, let me draw this clearly then. So suppose you have this block here, right, and you have, let's say, R1 and R2, and you want to pull this block out so that there is nothing on the output side, okay. There is nothing on the right hand side of the summer, there is no block on the right hand side of the summer. So what do you do then? Well, you notice that this is nothing but G times R1 plus R2. So therefore, if you don't want the block here, you better put it on the input side, both here as well as here, right. So that is another equivalence, right. So this is one trick you play around with the summer. If you want to push or pull out blocks on either side of the summer, these are things you have to do. At the same time, for example, let's say there's a pick off point here, okay. So how should I draw it? Okay, let's say there's this G here, and let's say there's this pick off point here. So this one goes unadulterated, this one goes through some G2, and let's say this one goes through some G3, okay, and this is your R. So notice what goes through each channel. Through this channel you have purely just G times R. Through this channel you have the G times R being multiplied by G2, so it is G2. So this is basically G2 G times R, this is G times R, and this is G3 G times R through each of these channels. So if you want to now replace this, okay, with an equivalent diagram where there is nothing on one side, on the left hand side of this pick off point, then you have to basically push this G on the right hand side. So what you then better do is you take this pick off point here, put in a G here, put in a G times G2 here, and put in another G here, G3 here, okay. So these are equivalent. So you can play around like this by pulling out and pushing in stuff on either side of the pick off points as well, all right. So that is another technique that we often need to employ in order to play around with these block diagrams. Remember, the ultimate goal in most cases is to eventually get to this unity feedback configuration, from which we can then make claims or statements about the performance of the overall system, okay. Needless to say that this also aids us in designing the controllers, which we shall see later on when we study things like root locus, okay. All right, but again there are a lot of promises for the future, but even in and of itself I hope that you see that these are interesting things to do, okay, interesting exercises, not very difficult, not very challenging, but nevertheless these are interesting things to do. So with these basic set of tools that you might have learnt about how to play around with blocks, you should be able to reduce most really complicated looking block diagrams if you are just mindful of what the operation is, right. Just be careful about those operations, be mindful of them, and you should be able to tackle most of these systems, okay. It's just about pushing in and pulling out these blocks suitably, or their reciprocals, right, in a proper fashion. You've already seen one rather involved, not very involved, but one rather useful application of this sort of technique where you see when you have a non-unity feedback loop, you want to convert it to a unity feedback, this is how you go about it, okay, purely from a block diagram reduction point of view. Okay. Of course, for those of you who are more interested, as I said in the previous lecture too, you should really go through Mason's gain formula for signal flow graphs, okay, and maybe you will learn a trick or two there from there as well. But for our purpose of this course, we will not cover SFG and Mason's gain formula. All right. So now, having seen all of this, let us not deviate or let us not digress too much from what the basic objective of all of this is. What is the basic objective? Recall that we will eventually be given a plant like this, right, which can be affected by a process noise such as this, which can then be also affected by measurement noise such as this, right. Remember, this is my output of interest. Now, my job is that given that I am allowed to place a controller CS at this juncture, yeah, my goal should be to minimize the effects of all of these. In fact, there is something I have not spoken about in the previous lecture, but it also does appear. There is something called a load disturbance. Remember, this is process noise, this is measurement noise, this is of course the plant, again I am dropping the S for want of space, and what you might also have every now and then is the appearance of something called a load disturbance at this point, okay. Okay, yeah. So now, in the face of all of these undesirable signals, which is the load disturbance, so let me just call it the load, alright. So the load disturbance L, this process noise and the measurement noise, you have to still make sure that this Y faithfully tracks this reference input, that is R, and all of this has to be accomplished by designing this controller. So that is the job of the control engineer. Remember where this D and S and NS are coming from? Because of inadequate modeling, okay. We cannot account for every single thing in a model, in a systems model. So we have to make leeway for that. So that is why we accommodate these process noises and measurement noises and say that, okay, fine, this is where we draw the line between accuracy in modeling, and now we let these process noises and measurement noises account for the inaccuracies or the uncertainties in the system. And then it is the job of this controller to robustify this system in the sense that despite the presence of these process noise and the measurement noise and this load disturbance, the reference signal RS should still be tracked well enough by the output signal, that is YS, right. So often you will encounter situations where having merely one controller here is not good enough. So then people often talk about things like 2 degrees of freedom controller, okay. We will probably not have time for these discussions in our course here, but it is good to know, right. So you might often have to employ multiple controllers at multiple places in this entire loop, right. So you will have more parameters to play around with, more controller parameters to tune, and therefore you should be able to do better. So the more the requirements from the system, you should have more variables, more lax variables to play around with, yeah. Otherwise you might only be able to do so much using just one controller having so many parameters, okay. So typically these controllers are of the type like P, PI or PID, which stand for proportional controller, proportional integral controller and proportional integral derivative controller. Don't worry if you have not heard of these terms, we have not even introduced them in this course yet, but just for the sake of name dropping I am just mentioning them here at this juncture, right. So now remember what our goal was, to bring us back on track. Here is what we want to study, okay. Given any system, we want to bring it down to its bare essential, that is this unity feedback structure, and then study what sort of a controller will enable us to meet all our performance objectives. What are our performance objectives? Remember, we have already studied some of the performance metrics for second order systems, right, such as percentage overshoot, settling time, rise time, so on and so forth, right. Now apart from that, we are now imposing certain other conditions, such as the fact that this error, okay, this error must also go to 0. Okay. Again, to reiterate, all of this requirement and all of these demands are valid only if the system is stable in the closed loop. If not, none of this makes any sense. So do remember that. Once you have learned sophisticated techniques of checking the stability of a system, you should never jump into the solution of a problem without first checking whether the system is at all closed loop stable. Yeah, you might be in for a rude shock. You might have designed all the things nicely and you might feel it should work, but then suddenly you simulate the system and things blow up. The reason being that you haven't checked for the closed loop stability. Okay. As of now, because we haven't taught you the techniques for checking stability, we will make do with just learning the tools for analyzing the performance. But later on, you should always check whether the system, in fact that is the first thing you should check, whether the system is stable in the closed loop. Alright. So now given that this is the configuration, what we want to do is we want to study what this error signal is like, and ideally, if possible, to design a controller that will bring this error to 0. In other words, what I mean is this Laplace inverse of this E of s is Et. So we want Et to tend to 0 as t tends to infinity. That is one demand. The second and the other demands are that effects of Lt, which is basically the Laplace inverse of this L of s, Lt dt, which is basically the process noise, and n of t are rejected soon enough. Okay. So these do not have a significant impact on our system. That is our goal. So okay, these are nice ambitious goals to set for ourselves while designing controllers. Alright. So now how do we study this? Let us for the moment cast our attention on this first point itself. Later on we shall also see this thing about this, how to reject this load disturbance and other things. Okay. Mainly we will concern ourselves with this, because as I said, the study of this D and N will involve delving into robust control, which is really beyond the scope of this particular course. Okay. So we will more at most deal with the behavior with respect to this reference signal and with respect to some load that is being applied, how soon we can reject this load. Okay. But remember, in the long run, a control systems engineer should be able to address all of these requirements. Okay. So with that goal in mind, now we venture forward into studying this kind of systems. But now notice that you cannot possibly check for the kind of error that arises for all possible kind of inputs. So therefore, we set before ourselves a humble goal, not a very humble goal, but a sort of a humble goal in the sense that we only test for Et as t tends to infinity for some special test signals. So what are these special test signals? It is a unit step, then there is this unit ramp, okay, t times 1t, and then there is this unit parabola. Okay, so these are our 3 test signals, and with respect to these 3 test signals, we check whether a particular system is able to reject these load disturbances and also track this reference input. Okay, that is going to be the goal before us. So remember, if I may summarize this for you, first, before endeavoring on any of these missions, always check for closed loop stability. Okay, always check for closed loop stability. Unless you check for closed loop stability, none of this study will make any sense. Second point, ensure that the system has been converted to a unity feedback equivalent. Remember, if someone gives you a system like this, with a non-unity feedback, okay, so let us say G1, do not, I repeat, do not make the mistake of evaluating this. In fact, we will distinguish this as the actuating error, okay, not the actual error, this is the actuating error. So, E of AS is not the same as ES unless G1 of S is equal to unity, alright. So, the first thing that you should do, or rather the second thing after checking stability, is ensure that you have converted this into its unity feedback equivalent like we had done here. And once you have reached this stage, now you can begin to talk about this error signal here, yeah, and study whether it goes to 0 eventually as t tends to infinity. Okay. So, remember these two steps that you must always perform. And the third thing is, now in addition to this reference tracking, if someone also puts in this load disturbance signal like we have considered here, so if this load disturbance signal also comes in, then you need to also be able to reject that load disturbance. Okay. So, find out the transfer function between R and Y, find out the transfer function between L and Y, and see that what sort of a controller, okay, what sort of a controller will allow you to track the reference and reject the load. Okay. That is basically going to be the goal of the overall system. Now, at this point, you see, without much thought, let me just put this G here, and let us say I am going to use just a proportional controller. So, the simplest kind of controller there is a static controller. So, C of S is nothing but K. So, it is not even dependent on S, okay, it is just a constant K. So, this is called a proportional control. Proportional control, all right. So, it seems like, it appears like it is a good idea, is it not, that if I increase the value of this K, why? Notice, okay, let me also bring in this here, let me bring in the load disturbance here, yeah. So, notice what is the transfer function between the load and the output, again what is there in the forward path, it is G. So, it is G, in one shot I will be able to do this without even computing those intermediate, doing those intermediate computations, right. So, I am going to, it is because of superposition is applied, so I am going to consider R to be 0 when evaluating the transfer function between L and Y. So, it is going to be G upon 1 plus Gk times L plus, so this is my Y, alright, plus Gk upon 1 plus Gk times R, alright. Now, it seems quite a good idea. What if K is very large? Yeah, look at this. If you make K very large, this, so Gk by 1 plus Gk is almost unity, which is what we desire. And what about this? G upon 1 plus Gk tends to 0. So, apparently very high proportional gain will allow us to do this, right, allow us to kind of reject the effect of this load disturbance and also to eventually have perfect reference tracking. So, what then is the impediment? Why all this business about designing controllers and all? Why is this such a complicated affair? If a simple proportional controller which is not even dependent on S can allow me to meet my objectives, why do we study all these sophisticated techniques? And therein lies the catch. You see, that is something, the elephant in the room we have not addressed and we kept on postponing, but not for long now, which is the question of stability. You see, when you talk about this closed loop system, it is the roots of 1 plus Gk is equal to 0 are closed loop poles, alright. So, now notice that Gs is nothing but some numerator polynomial divided by some denominator polynomial. So, these are, this is a polynomial, this is also a polynomial typically, alright. So, now if you use Now if you use this k, this 1 plus k times ns upon ds is equal to 0, and you want to solve for this, notice what happens when k tends to very large values. What you are essentially solving then is ds plus k times ns is equal to 0. Okay. Even without too much sophistication, you can guess that as k becomes very large, basically the roots or the solutions of this equation is tantamount to, almost tantamount to solving for ns is equal to 0. Now recall that even if your open loop system G is stable, yeah, there is no restriction on its zeros. When we are talking about stability of the open loop system, we are only concerned about the roots of ds. Okay, we are only concerned about the roots of ds. But what about the roots of ns? They could very well be on the right half plane. For instance, when you have a non-minimum phase system where the zeros are in the right half plane. In such a case, right, you would expect that as you increase k, you will have some of your roots in the right half plane. Of course, we will do a much more detailed study of this when we talk about, when we discuss root locus, yeah, and subsequently immediately after this next few lectures we will be talking about something called a Routh-Hurwitz stability criteria. There also we will see that if you increase k, it is in general for higher order systems going to lead to instability. So that is what prevents us from employing, this apparently or seemingly good idea of using very high values of k in a proportional control setup like this. Okay. So that is why we should be a little more careful and we should devote some attention towards the study of systems, okay, or the errors of the systems for these different types of inputs. Okay. So now let us say you have system configuration like this, suppose it is uncompensated, alright. So again we want to first ensure how good or bad the uncompensated system is, and then we will know what basically the controller is required to do when it is put in place here, somewhere here. So notice, what is this transfer function? We have already derived this, yeah. If we call this variable es, we have seen that r minus y is equal to e and g of e is equal to y. So g of r minus y is equal to y, from where we have seen that, right, from where we have seen that y is equal to g by 1 plus g r, right. So therefore what is E? E is equal to y, so let me write that a little more detail. So r minus y, so let me not do it in one step. So what is r? R is just like as it is, minus g upon 1 plus g y, sorry, r. So let me pull this r out. So it is 1 minus g upon 1 plus g times r, which is nothing but 1 upon 1 plus g r, which is basically what we saw as a sensitivity function. Okay, right, not a big deal. Now it turns out then that if we want to find out, to evaluate Et as t tends to infinity, can we apply final value theorem? Well, of course. Why? Because implicitly we have assumed that the system is, as I said, for now we have postponed the discussions of stability. So implicitly we have assumed that the system is closed loop stable, and if it is closed loop stable, then to a closed loop stable or any stable transfer function for that matter, we can always apply the final value theorem, right. And we have also defined before ourselves what the problem is, which is like we want to study for 3 particular test cases. So what are basically those test cases? We have this the unit step, the unit ramp and the unit parabola. So the unit step has a Laplace inverse of 1 by s, the unit ramp has 1 by s squared, and the parabola, let us say, it's t squared by 2, so it's 1 by s cubed, right. So for these three test signals we want to find out, these could be our potential candidates for RS. Yeah, we want to find out this E of s is equal to 1 upon 1 plus GS RS. So if you want to apply the final value theorem, so E of t as limit t tends to infinity, because we are assuming, again I repeat this so many times at the cost of boring you, that this is all under the assumption that it is closed loop stable, otherwise none of this works, okay. So we consider this here, this limit Et as t tends to infinity is equal to nothing but limit s tending to 0 s times 1 upon 1 plus Gs times Rs, okay. So now sequentially we will apply these. So for unit step, what do we have here? We have that this is limit s tending to 0 or E of infinity, with a slight abuse of notation if you permit me. This is s tending to 0, 1 upon 1 plus G0, provided G0 is not indeterminate, that is Gs does not have any poles at the origin. If Gs has a pole at the origin, then I cannot evaluate G0, is it not? What will happen then, in fact, if Gs has a pole at the origin, notice what happens, this G0 will then tend to infinity. So then therefore, if Gs has no poles at origin, let Kp is equal to limit s tending to 0 g of s, okay. So this is the definition. So if Gs has no poles at the origin, Kp is equal to constant E of infinity is equal to 1 upon 1 plus Kp, which is also a constant, alright. Now on the other hand, if G of s has one or more poles at the origin, then limit s tending to 0 G of s tends to infinity, right, which means Kp tends to infinity. Therefore, E of infinity, again with an abuse of notation, what will happen? Notice that if k goes to infinity, if Kp goes to infinity here, then this E of infinity goes to 0, right. So this goes to 0. In other words, what we have just discovered is that for a step input, if your open loop equivalent transfer function, and I use the term equivalent, note, why? Because your original plant might not be in a unity feedback configuration. If not, then you have to bring it down to this unity feedback configuration using the methods of block diagram reduction we have shown, and then apply this final value theorem not to the plant transfer function, remember, but to the equivalent forward transfer function in the unity feedback configuration. Very important point, okay, one of the most common mistakes that students often make, right. So what happens is then, you see that the moment you have one or more integral modes, that is poles at the origin, you see that the error due to, the steady state error due to a unit step will always go to 0, okay. So that is an interesting phenomena that we have now noticed. If you think about it a bit, it is not very surprising. You see, what are we basically saying? If you have an integral mode here, what does the integration do? You see, the moment that r minus y becomes 0, if there is no integration, right, then there is no input going into this plant, and so therefore again the output at this terminal will tend to reduce. The moment this reduces, this fails to catch up, this y fails to catch up with r, and then again this E becomes non-zero. So this process goes on and on, like they're trying to catch up and they're trying to again fall over, again catch up, again fall over. On the other hand, if there is an integral mode here, what does the integration do? Even when this E is 0, remember this integration has actually remembered, it's a memory. It's a memory of all the errors that have been integrated over time. So even if the instantaneous error signal is 0, but if there is an integration or an integrator present in the plant itself, right, then because of the non-zero error in the past, the error signal, the signal which is coming out of this plant will not go to 0 immediately as soon as this E goes to 0, okay, and therefore it will not let this signal fall. And so an integral action helps in maintaining maintaining zero steady state error, okay. So therefore we already have a partial answer. You see that idea that we had, that if you keep increasing this proportional controller's gain k, which seemed like a good idea here, we saw that you might run into trouble with stability. But now if you have an integral action instead, now if you use an integrator here, of course the stability might still be an issue, but in general if you use an integrator here, it turns out that now you can kill off this steady state error, yeah, and maybe there is hope that you can also address the stability issue, okay. So now we have answered this question for the step input. Hopefully we have understood this well enough to now be able to deduce what happens to this steady state error to a step input, right. Now for a ramp, so let us say now Rs is equal to 1 by s squared. So then what about E of s, limit s tending to 0, remember that is the final value theorem after all, is it not? Yeah, right, okay. So this is going to be nothing but equal to s times 1 by s squared times 1 upon 1 plus Gs. Do check, this is coming in because of the Rs, this is coming in because of this final value theorem statement here, and this is of course the sensitivity function. So now what happens, what we have is 1 upon, of course with limit s tending to 0, s plus s Gs limit s tending to 0 is equal to 1 upon s Gs limit s tending to 0. So suppose we name this as Kv, Kv is equal to limit s tending to 0 s Gs, alright. Now suppose we are given this, okay. Now what can we deduce? Now notice that if Gs has no integral mode, what happens then? Are we or are we not in trouble? Of course we are in trouble, because if Gs has no integral mode, then G of 0 is a constant. So therefore Kv will go to 0, implies Kv is equal to 0, and if Kv is equal to 0, then notice that E of infinity is equal to 1 by Kv. So for G of 0 constant, we have Kv is equal to 0 and E infinity is tending to, shouldn't write equal to, so E of infinity, the steady state error tends to infinity. So if you have a plant with no integral modes, alright, and if you are applying a ramp input to it, yeah, your steady state error will be infinity, infinite. On the other hand, suppose Gs has one integral mode, right. So suppose Gs has one integral mode, then what happens? Then Gs can be written as some G bar s upon s, where G bar 0 is constant, okay. So this is what G of s is then, right. In that case what happens? Notice from this previous description here, S times Gs is going to be nothing but G of 0. So, in that case Kv is equal to G bar 0, which is a constant, and therefore E of infinity is equal to 1 by Kv, which is also a constant. So, this is not as bad, but nevertheless this is still an error. Now, notice in many textbooks they would instead of calling this like error, they would call this a percentage error. In my mind this is an abuse of notation, because in case of a ramp input, you see ramp keeps increasing, there is no steady value to which it settles, okay, unlike a step which actually settles at a steady value of unity. So, there you can talk about this percentage error. So, if your steady value is 1 and if you are settling at 0.7, then there is a 30% error, for instance, alright. On the other hand, for this ramp, now what is going to be a steady value, right? So, what happens in such cases, if you look at the plot, for example, if this is your ramp and let us say your system's response goes like this, and then there is some error like this, and this remains steady throughout, yeah. So, this is basically going to be like 1 by Kv, yeah. So, sometimes people also call this as a percentage error, under the assumption that 1 by Kv upon 1 into 100, yeah, kind of an abuse of notation. So, do not confuse yourself with this notation. What they mean by percentage error is, so if someone says that percentage error is 30, you would immediately read off that 1 by Kv is 0.3, yeah. So, that is the information that they are trying to convey, but to my mind this is not how it notationally we should call it. We should not call it a percentage error, we should just call it a steady state error, which is 1 by Kv. Now, notice if G of S has more than one pole at origin, then what happens? Then we might be able to write it as G of S is equal to some G bar S upon S to the K, where G bar of 0 is constant. Now, notice what happens. Now, if you apply limit S tending to 0, right, S times G of S is always going to be some 1 by S to the power K minus 1. Of course, we have not mentioned here. So, K is greater than 1, all right. So, K is greater than 1 times times G bar of S, limit S tending to 0. Now, we know that this is equal to nothing but G bar 0 limit S tending to 0 1 by S to the K minus 1, and this tends to infinity. So, if this tends to infinity, notice that if this tends to infinity, what happens to the steady state error? So, therefore, Kv tends to infinity. So, 1 by Kv, which is basically the steady state error, yeah, this tends to 0. So, that means that if your system has more than one integral mode, then your steady state error due to an ramp input will go to 0. By the same token, now if you check for the parabola, right. So, let us say your Rs is now 1 by S cubed, okay, and suppose G of S has one or no pole at origin, all right. Then what do you call it? What do you know about the steady state error? What can you say about the steady state error? So, then that means you have essentially some G of S is equal to at most 1 by S times G bar of S, where G bar of 0 is constant, all right. So, then what you can say is that limit S tending to 0 S E S is equal to limit S tending to 0. Of course, there is this S because of the final value theorem, there is this 1 by 1 plus G S because of the sensitivity function, and there is this 1 by S cubed. So, this S will cancel out and this will become S squared, right. So, therefore, it will be 1 over s squared, limit s tending to 0, s squared g of s. Yeah. So, we call this 1 over k a. So, this k v we call the velocity constant, the k p that we had defined here, this k p we call the position constant, and now this k a is what we call the acceleration constant. Okay. So, notice that the steady state error is inversely proportional again to the acceleration constant, just as it was inversely proportional to the velocity constant and the position constant in case of the ramp and the step inputs respectively. So, in case of the parabolic input, it is inversely proportional to the acceleration constant. It is again straightforward to check in the same method that we using the same method that we have applied earlier, that if a system has 3 or more poles at the origin, right, if a system has 3 or more poles at the origin, then we can say that the system's steady state error due to a application of a parabolic input will go to 0. On the other hand, if a system has exactly if a system has exactly 3, so I would say 3, more than 3, if it has more than 3, then it would go out. Okay. If a system has exactly 3, what happens then? Then also we see that g of s, we can factor out 1 by s cubed, so this will go to infinity. So, k a will go to infinity, and therefore 1 by k a will go to 0. So, therefore, the assertion is like in the previous case here, yeah, if Gs has more than 2 poles at origin, the value of E infinity goes to 0 for a unit parabolic input. On the other hand, if it has only 1 pole or no poles at the origin, then the assertions, the claims will rather change. Okay. If it has exactly 2 poles, what happens? So, then let us take this consideration. So, Gs is equal to 1 by s squared times some g bar s, where g bar 0 is equal to constant. So, then let us evaluate this, limit s tending to 0, s E s is equal to limit s tending to 0, s times 1 by 1 plus g s times 1 by s cubed. So, this is going to be nothing but 1 by s squared g s limit s tending to 0. So, what is s squared g s? S squared g s is nothing but s squared upon 1 by s squared times g bar s. So, if you let limit s tend to 0 here, this is going to be a constant k a. Okay. So, then k a is constant. Okay. So, therefore, your E infinity will be 1 by k a, which is a constant. So, therefore, if you have exactly 2 poles at the origin, then the response due to an application of a parabolic input will show a constant steady state error. If you have more than 2 poles at the origin, then the steady state error will be 0. If you have less than 2 poles at the origin, then you will notice that the error will blow up. There will be infinite steady state error, because k a will go to 0 under such circumstances. Exactly using the same methods that we have shown so far, you should be able to derive those results. So, incidentally, before we close this lecture, I would like to define this term. So, instead of repeatedly saying the number of poles at the origin, number of poles at the origin, we have a name for this. We call it the type of a system. Remember, the order of a system is the total number of poles of the system, right? The degree of the denominator polynomial. Now, we introduce another definition, which is the type of a system. Okay. Type of a system. So, the type of a system is the number of poles of the system at the origin. Okay. So, that is a type of a system. So, in that parlance, if we summarize what we have seen so far, we will see it in the form of a table in the next class. So, the last thing we are going to discuss in this lecture today is a summary of what we have seen thus far. What we have seen is, if a system is type 0, then the application of a step input results in a constant steady state error. The application of a parabola or a ramp will lead to infinite steady state error. If a system is of type 1, then provided the system is closed loop stable, the error due to a unit step will be 0, the error due to a unit ramp will be a constant, and the error due to a unit parabola will again be infinite. If the system is of type 2, right, then the error due to a unit step will be 0, provided of course it is closed loop stable. The error due to a unit ramp will be 0, the error due to a unit parabola will be a constant. For system types greater than 2, provided the closed loop system is stable, all the errors, whether it is a unit step, unit ramp or a unit parabola, all of your steady state errors will go to 0. Okay. So, that is the take home message. The more the integrators you add, the more the number of inputs for which your system steady state error will go to 0. We will see that in the form of a table in the next lecture. We will start with that and then go on to explore a few more topics until we address this fundamental question of stability. The first thing we will see is Routh-Hurwitz criteria, which will aid us in evaluating the stability of a system. That is all for today. Thank you.